Part 3 on JMESPath. This is where it gets exciting. We look at functions like length, people, max by, and we're going to look at a complicated example and go through that of a query. And then there is a section on JMESPath.org which is further examples, and we're going to look at some of those. So we've got a filter there within a multi-select list, and we've got a multi-select hash there. And then we're going to talk about specifying the consulting the JMESPath specification and how to read BNF, an interlude on ASCII, we're going to talk about that, and Bob Beam is going to come up. So first of all, functions. So we use curly brackets for collections of key value pairs, unordered collections. We use square brackets for arrays, and it's rounded brackets that get used for containing those arguments of a function. So we have the function on the outside to the left of the rounded brackets. So function expressions, we might have length and then people in the rounded brackets. And if we've got a people array here, which we do, it's got 3 objects in it. Let's have a think though. That's why I've put the bell. Is this going to be zero-based counting? So we've got, as you can see, objects, but are we going to go 0, 1, 2 and say that the length is 2? I can say we're going to return in the result a number, an integer. Is it going to be 2 or 3? Is it going to be count words or existence words? And so 3 objects, 0 first, second, so we're going to put it, no, it's 3. So 3 elements exist. I think that's intuitive that you use existence there, so I don't think that's too problematic. So here, people, you just put the name of the field. As you can see, it's just got one argument, one thing in the rounded brackets. Functions can be used to transform and filter data in powerful ways. The full list of functions can be found on the spec, and the function expression spec has the complete details. Below are a few examples of functions. The example prints the name of the oldest person in the people array. So this is a different function from length. How are we going to find the oldest person? Well, what we do is we use this max by function that has 2 arguments. You can see the arguments separated by a comma within but both of the arguments are within the rounded brackets, and the result we'd get from that is just a. So let's break that down. So that's the key, people. It's people colon, whose value is an array. Age is one of the keys within each object. It's one of the properties making up a person, isn't it? And we've prefaced that with an ampersand symbol, and that's saying extract the maximum age value. But we're going to look at why exactly there's an ampersand there. There's not a full stop there because we use a comma to separate the arguments in a function. That's just the way it is. It's opening rounded bracket x, comma, y. And yeah, it's not a sub-expression. It's not that dot notation of a dot b dot c. It's not, age is not nested within people. We're providing 2 arguments to a function. Okay, and then it's dot name. After we've finished with the function, we've done the closing rounded bracket, and name is an extraction instruction. This is the field we must evaluate and print in the result. So we're not actually printing the value of max age, we're printing the name. Come on. So name an array, okay, people. And then we'll extract the ages, sort amongst them, settle on 50, but deliver the name in the result. Very nice. Okay, functions can also be combined with filter expressions. How is this going to work? Are we going to put the filter within the rounded brackets? In the example below, the JMESPath expressions finds all elements in my array that contains the string foo. So in my array, okay, so it's actually as if the function is within the filter. So we use a question mark to signal the beginning of the filter expression. The @ symbol is used for the current node. We'll have to explain that another time, but foo is the second argument there. We use that double equals sign, which is the equality test. Is foo at the current node set to true? And the function is the contains function, and we get back foo, foo bar, bar foo, everything with foo in it. The @ character refers to the current element being evaluated in my array. That will be clear, I think, obviously, if you look at the instructions for that particular function. So it seems that like it deals with every element in the array one at a time then, doesn't it? The expression contains @ comma foo. That expression will return true if the current element, because the things in an array are called elements, if it contains the string foo. While the function expression spec has all the details, there are a few things to keep in mind when working with functions. The arguments do have types. If an argument for a function has a wrong type, you'll get an invalid type error. There are functions that can do type conversions. The toString function, the toNumber function, and that will help get the arguments converted to their proper type. If a function is called with the wrong number of arguments, an invalid arity will occur. Logicians talk about the arity of operations. Is it unary or binary and so forth? You haven't got enough arguments. Now we're going to look at a couple of further examples. Here we've got a multi-select list. You might recognize this from earlier. We've got name, comma, state name. So we're extracting from the name key and we're extracting from the state collection, because it's state.name, the dot because there is no value that's just laid out next to the state key. We have to do .name. And we can take this further by installing a filter expression in those square brackets so that we want the age to be bigger than 20. So if we ask for the age to be bigger than 20, we're not going to get Bob. We're only going to get Fred and George in the result. Filters and multi-select hashes. In the previous example, we were taking an array of hashes, a list of hashes, and simplifying down to an array of two-element arrays containing a name and an age. We're also only including list elements where the age key is greater than 20. If instead we want to create the same hash structure but only include the age and name key, we can instead say people, age must be bigger than 20. We provide those instructions on the right, name and age. So just like we inserted a filter into the list before, the multi-select list, we're just doing the same here. So the last half of the above expression contains key value pairs which have the general form key name, colon, and then the expression. And I often call that last half the instruction. In the above expression, we're just using a field as an expression. But they can be more advanced. There can be more advanced expressions. For example, next to our label tags, because we want tags to be the name of the field we're creating in the result, we could have only the 0th tag selected. So that's our selector, tags 0. Notice in the above example, instead of applying a filter expression, we're selecting all the array elements via asterisk. So that's the result that would be generated there. You can see that we're only getting the first of the tags element A here, D from here, and G from here. It'd be interesting to see, can you put anything in your selectors here within the instruction period portion? Now we're going to look at a complicated example. We've got a lot going on. Let's break this down. First of all, just the data that we're querying. We have seen this before. We've got reservations, and these are objects within an array. Okay, so here's a reservation within an array. The value of instances is of course an array as well, and we've got a list of instances, so an array within an array ultimately. Well, no, I wouldn't say array within an array, that's a bit misleading. And then each instance has a number of properties. Each instance has a type, a state, tags. So let's look at this. Let's break this down. What's between the dots? That's a good way of doing it. So we've got here, there, we go up to the next dot, we go up to the third dot. Can we see it looks like we're then using the pipe expression, but hold on a minute. Where did that closing square bracket at the end get opened? Okay, let's start again. So there's the opening square bracket, there's the closing square bracket. So the overall structure after that green block is dot and then thing in square brackets. And that signifies, what does that signify? Dot something in square brackets. It's instructions, isn't it? It's the second portion are instructions for so it's a multi-select list. So let's home in on just what's in the blue, alright? So we're homing in on that right hand side. Here we go, there we go. We can see a filter expression here. The question mark signifies the beginning of it. It says tags just before their square brackets. So that must be the name of a field, tags, right? And the filter is qualifying our selection within tags. So it's that general pattern, field, square brackets. But then this is also a field and then square brackets. That's fine, values and then something in square brackets. So I know there's a key called tags, I know there's a key called values, just from looking at that field square brackets pattern. And what does that dot tell us? Well, it tells us that the values key is within the tags key, so as we move from left to right. So we have a projection here. There's the pipe, and we're going to pipe the output from the left hand side into the right hand side. So the output from the left is going to be our input. So there's that structure within the red line, field dot field. And what do projections of this sort output? What do we get from a projection? Do we get an object? No, we get a series of values. We get an array coming out of that. We package them into square brackets. It's quite hard to make sense of that 0 in square brackets. Pipe the output into an index expression. How does that, what are we even saying there? Well, the index expression is selecting the 0th element of the array which we output. Okay, fine. So in a way, that's all one thing I've just shown there. Remember, overall it's a multi-select. So we've got 3 elements, bang, bang, bang. They're the 3 things we're selecting. And that comma is at the same level as that comma. So going back to this data, we've got instances whose value is an array. I've just marked up the opening square bracket and closing square bracket in pink there. There's one instance, which is a hodgepodge of properties. There's a second. I've marked up the 2 objects with green. I've put green on the curly brackets. And the 3 properties which make up the hodgepodge of properties are type, state, and tags. Okay, type, state, and tags. If we look at tags now, that value is also an array. Tags consist of a key and a value. So here, this first instance has got 2 tags because it's got 2 keys and values, and that's what tags are. They're combinations of keys and values. Okay. And what's interesting here, I think, is that sure, key is just key, colon, name, but the value of values, okay, there is a key called values, is actually an array. So you can have more than one value for a particular key. Okay, so they're using one of the tags to be the name. Not all of the tags on an instance of the name, but one is name. So it's key, name, and then the values are like web, or it could be web, comma, database, comma, app, because remember we're using an array here. Okay, this means that any projection that evaluates values is obligated, it must include an index expression, otherwise it would be an indeterminate index. Hence, that's why we get this 0 after the pipe expression, after the pipe here. Lovely. But that's wrong, that line of thought, because actually to lock down this, okay, the value of values, that array, we're actually going to use these square brackets here. Okay, so what's the role of this then, after the pipe expression? Well, this operates on the whole JSON. So, let me explain. So it hoovers up all the key fields whose value is name, generating an array. Okay. Because such name keys are always in the 0th position. Okay, so if we look at the value of tags here, we've got an opening square bracket, and then we have the first object, which is consisting of a key and our values. And what this index expression here is, these blanked out square brackets are settling upon the first tag, not the first item within the values list, but the first item within the tags list. And for this one, the first item within the tags list. I think that's right. I'm not completely 100% sure, but I think that's what's the role being played by these blanked square brackets. And so the assumption is that we're going to have the 0th element in the tags array be the name key. Otherwise, this will all fall apart. And we've got that principle, the index is internal. So here we can count within the tags key 0th first. Within this tags key, 0th first, 0th first. Because we only want to generate one at a time, that's what the red arrow one is doing, I think. Remember, it's a multi-select overall, so we need one thing to package into the array. Okay, so that the 0 in square brackets is part of the first selector. But we'll have to come back to that. Okay, another example, filtering and selected nested data. In this example, we're going to look at how you can filter nested hashes. So we've got people, $general.id, and we want that to be equal set to 100. .general, and then we're piping the array that we get, or subjecting the array that we output from that to the index expression, which is a 0 in a square bracket. So what have we got here? We've got people, colon, and then an array. General has this hodgepodge of properties next to it. There's a hash. Why is it nested? Because general is within square brackets, so it's a nested hash. So people, $general.id, so that's going to go to general. Look within general, we see the ID, and as you can see, if you look at the data, how many have ID equals 100? Only one. And then if there is more than one, we only take the 0th. I don't see why we need that 0 in square brackets. And it's true, I mean, let me explain why. So when we say general.id, the ID must be 100, well, that rules out this object down here, okay? Because that's an ID 101, so that collection goes out the window, consisting of general and history. That's one collection. And we're not interested in the history key, which is the second element of the hash. Well, good news, we've put .general there. So what else do we need to do? Why do we need 0 in square brackets? The tutorial says, in this example, we're searching through the people array. Each element in this array contains a hash of 2 elements, and each value in the hash is itself a hash. We're trying to retrieve the value of the general key that contains an ID key with a value of 100. If we just had the expression people general ID must be, is it 100, we'd have a result of that. Okay, we understand that, don't we? So we've got the general and history there, those 2 keys. Let's walk through how we arrived at the results. In words, the people general.id set to 100 expression is saying, for each element in the people array, select the elements where the general.id equals 100. If we trace the execution of this filtering process, we have first element, and we've got general and history, so it's ID 100, age 20, and we apply the expression general.id to this hash. And we just come back with the value, we evaluate it, get 100. Does 100 equal, is it set to 100? True. Add this first element to the result list. Second element, we assess that. If we apply general.id, we get it's 101. Is 101 equal to? So on the right hand side, we say the thing we're applying to it. No, that's false, so don't add that to the list. So we've only got a list containing the first element then, because that didn't go in. So this isn't the final result though, we want just that. Okay, we don't want the history. So in order to get this value from our filtered results, we need to first select the general key. This gives us a list of just the values of the general hash. And can you spot the difference between the top and the bottom? We've just added square brackets at the bottom because index expressions pump stuff into square brackets, but yeah, and from there, oh no. Okay, so that's a result of applying the general key. Okay, so we haven't even, yeah, that's not to do with the index expression, the 0 in square brackets. From there, we then use a pipe to stop projections so that we can finally select the first element. Note that we are making the assumption that there's only one hash that contains an ID of 100. Given the way the data is structured, it is entirely possible to have data such as, and that is puzzling I find, we use a pipe to stop projections. stop it. What does it keep going? What do you mean stop it? But yeah, back to that question, why the index expression, it seems to play a trivial role, namely converting that into that. So we've just removed the square brackets, extracted it from the square brackets, but we're making the assumption that there's only one hash that contains an ID of 100 yet. So here's an example where we've got 3 people. 2 of the people have an ID of 100. Okay, so there's the array. So how would our query handle this? Well, obviously it would select both of those, okay? So we've got that filter. 2 of those objects get through, so we'd move those over here. That's fine. But then the result of that is an array. Remember, the question mark is tucked, which signifies a filter is tucked within square brackets. So what it outputs is an array. So we get those there. We've got the 0 from the first, and we can then pipe that to our filter expression, which lands the 0if. So that one, even though it's got an ID of 100, would be left out the final result. Note here that the first and last elements in the people array both have an ID of 100. Our expression would select only the first element that matched. Finally, it's worth mentioning there is more than one way to write this expression. In this example, we've decided that after we filter the list, we're going to select the value of the general key and then select the first element in that list. We could reverse the order of these operations. We could have taken the filtered list, selected the first element, and then extracted the value associated with the general key. So it's just saying that cutting it down, there are 2 keys, remember, general and history, and we can keep those lumped together when we extract the first item and then cut off one of them. So if we did it this weird way, you can see we can just tack on .general to the 0 in square brackets. Actually, never seen that before, actually. Yeah, you can just do 0.general. Okay, another example, and this is going to involve talk of an anonymous function. So an anonymous function, look, one other term for it is lambda function. Lambda expression, block, is a function definition. So you're defining it, you define functions in code that is not bound to an identifier. Anonymous functions are often arguments being passed to higher order functions or used for constructing the result of a higher order function that needs to return a function. If the function is only used once or a limited number of times, an anonymous function may be syntactically lighter than using a named function. So there's a contrast between anonymous and named. Anonymous functions are ubiquitous in functional programming languages and other languages with first-class functions, where they fulfill the same role for the function type as literals do for other data types. Anonymous functions originate in the work of Alonzo Church and his invention of the lambda calculus, in which all functions are anonymous, in 1956, before electronic computers. In several programming languages, we introduce anonymous functions using that word, lambda, and anonymous functions are often referred to as lambdas or lambda abstractions. Anonymous functions have been a feature of programming languages since Lisp in 1958, and a growing number of modern programming languages that support anonymous functions. Yeah, not a great explanation, but some context. Functional programming languages, we've got Haskell, Scala, and there's Alonzo Church. We don't really, I don't fully understand that. What do we mean not bound to an identifier? What does that mean? What is a function definition? What is an identifier? But anyway, if we look at a function like this, we've got sort by, which we've seen before, contents and date, and instructions for an array on the right hand side. Okay, those curly brackets are instructions for an array. We've got our labels and our selectors. Okay, so on the left hand side we've got some objects, the date property, a key property, and a size property. And I think the field called date, which you can see it's got a timestamp as the value, used to be called last modified because the example's been changed. It's just, that's going to matter for the explanation. And so think of this as, well, we're sorting the contents array by the value of each last modified key, which is the date key, in each element in the contents array. The sort by function takes two arguments. The first argument is an array. It's a whole array, and the second argument describes the key that should be used to sort the array. The second interesting thing in this expression is that the second argument starts with ampersand, which creates an expression type. Think of this conceptually as a reference to an expression that can be evaluated later. That does confuse me. If you are familiar with lambda and anonymous functions, expression types are similar. So the reason we use ampersand last modified instead of just last modified, right? Why isn't it opening rounded bracket, argument 1, comma, last modified? Well, they say it's because if the expression is last modified, just last modified, it would be evaluated before calling the function. And given that there is no last modified key in the outer hash, the second argument would evaluate to null. Okay, so it's to do with the fact that the two arguments, I think, the two arguments are picking out different things. The first argument, which was just contents, is naming the key which has an array as its value. So we need, I think that's the idea, we need the function to home in on that first, and that's why they say there is no last modified key, which is on the inside, or the date key. There is no last modified key in the outer hash, so we need to hold off before evaluating that last modified key. Also note that we're taking advantage of the fact that the dates are in ISO 8601 format, which can be sorted lexicographically. Okay, so they say the second argument starts with ampersand, which creates an expression type. Okay, so we're sorting the contents array by the value of the date key, or last modified. Doesn't mean they've changed the example. Okay, so the ampersand creates an expression type. That we have got an object right on the outside. That's the outer hash. The inner hash, well, these are inner hashes. So the structure is contents and then square brackets. Okay, and so on. There are 6 objects. So the reason we use ampersand instead of last modified is because if the expression is just last modified without the ampersand, it would be evaluated before calling the function. So we somehow want to call the function and then evaluate it. That must be. The function ranks the dates. So surely the last modified key does need to be evaluated, right? So it is a bit confusing to me, that. But they say there's no last modified key in the outer hash. The second argument would evaluate to null. I think they mean second argument. Okay. So we want the function to hold off. Both of these things seem to be cited as a reason for the ampersand. We don't want it to be evaluated before calling the function, and it's also the fact that the key is not in the outer hash. So the conclusion I'm drawing is that the function we somehow call the function and then we evaluate. What's this doing? Well, if we put 1 instead of an asterisk, we'd just get the first, not 0f, key and size, as you can see. So it's selecting among the objects in the contents array, that asterisk. We could put a slice there, 0 up to 2. And there are our instructions. We want a field called key and a field called size. Okay, now let's look at how we might read the JMESPath specification, or consult it, or any specification, because it's actually not straight off the bat readable. It's intimidating. It contains things like that. What's going on? And that. What is that? It's so unfriendly. It's so ugly. But it's because we're moving to a high level of abstraction, so it's a meta language. We're trying to reduce everything you can do in the language, so we might say everything you can say, to a set of rules. Here is John Backus talking about how he came up with the language that's used in the JMESPath specification, which is called BNF, Backus Nower Form.
I had come to one of these meetings with this BNF descriptions, a little paper, and I handed it out. I hand carried it because it was so late in the game.
Right.
So I had these copies that I dragged to the meeting and passed out to people.
Yeah.
And nobody paid any attention to it.
Really?
No, and except Peter Nower.
Ah.
And when he came to write up a thing, he used this descriptive method.
Yeah.
And improved it in the process.
In retrospect, I can't imagine specifying a language without using BNF. So what were they doing before that time frame? It must have been
they were
very muddled.
Just writing English.
Wow.
Yeah.
So if we go to the JMESPath specification, you'll see this. They say grammar, where grammar is, think of it, although you might think of grammar as just lists of verbs, like in a language like Spanish that you might learn at school, just lists of verbs. Yeah, lists of verbs with the different conjugations, like I think, you think, they think. They kind of are rules there, but they really are rules here. And so they say the grammar is specified using augmented BNF as described in this request for comments RFC 4234. So ABNF, augmented Backus Nower form. And here's RFC 4234, and they say it's been obsoleted, it's useless now, by 5234. There's a new one, 5234, and the authors are David Crocker and Paul Overell, and they say this document specifies an Internet Standards Track protocol for the Internet community and requests discussion and suggestions for improvements. Please refer to the current edition of the Internet Official Protocol Standards. So this is 2005. There's a few different ones. There was one before 4234. As we know, we've got 5234, which came after. It's copyright 2005. But this happens to be the one that was used in JMESPath, so we're going to have a look at this, because it's an important, helpful thing to know. So these are the contents. There's a section on rule definition. There's a section on the operators. The operators are symbols like plus and minus in maths. And then they actually use ABNF to define ABNF. There's a section called security considerations, where they just say, seriously, there's not really anything we need to say here. It's just not part of this discussion. And then references. So we won't go too deep here, but it's not too complicated. The BNF starter pack, symbol, rules, where a symbol means it's the opposite of a terminal. So a symbol is like, it's got to be broken down. It's begging to be broken down into something smaller. What does this have to do with defining a language? Well, the language defined by the BNF grammar, which is going to be a set of rules, is nothing but the set of strings you can produce by following the rules. So that's why describe a language using rules. So it's reductive. The rules are called production rules because they produce the strings of the language. Let's look at a production rule. There it is. Symbol. That's where the symbol would be. Colon equals alternative 1, vertical line, and then alternative 2. Okay, so we have alternatives either side of this vertical line. It's not the pipe operator from JMESPath. So what's being said there? Notice the colon equals. The production rule is saying that the symbol on the left must be replaced. It must be replaced by one of the alternatives on the right-hand side. And we separate the alternatives with the vertical bar. Alternatives can in fact consist of two things, symbols or terminals. Okay. Yeah, so that means the right-hand side of a symbol, we might find another symbol. Now, to really understand that RFC, we need to briefly look at some ASCII. Great thing. It stands for the American Standard Code for Information Interchange, ASCII. All the characters used in email messages are ASCII characters, as are the characters in hypertext markup language documents. But in 1960, there wasn't any standardization. IBM, where John Backus worked, IBM's equipment alone used 9 different character sets. They were starting to talk about families of computers which need to communicate. I said, hey, you can't even talk to each other, let alone the outside world, says Bob Beamer, who worked at IBM from 56 to 92. Midway through Beamer's IBM career, this heterogeneity became a real concern. So, in May of 61, Beamer submitted a proposal for a common computer code to the American National Standards Institute, ANSI. So ANSI sorted out ASCII, and the X3.4 committee, chaired by John Auwerter, was established and got to work. There's Bob Beamer. Go to ASCIIcode.com, where you'll find a table like this, which tells you a decimal character for each symbol. Look at this column, we've got symbols like CR and LF, and there's a binary number as well. You've got those 8 bits. And look here, the description of this one is line feed. The symbol is LF, we've got carriage return down here, symbol is CR, so line feed and carriage return. Now the hexadecimal for line feed is 0A, new line A, carriage return 0D. Double quotes. Just quickly one more, the hexadecimal is 22, so this is a great quote from a duck once, quack quack. So hexadecimal is 22, and a lowercase z is 7a in hexadecimal. But it's also 122 in decimal. Okay, so that's how it works. So we're now prepared to read RFC 5234. We said there's a section on rules and operators. The name of a rule is simply the name itself, that is a sequence of characters beginning with an alphabetic character and followed by a combination of alphabetics, digits, and hyphens. Rule names are case insensitive, and this will come up again and again. So rule name with an initial capitalization, all caps, all come back to the same rule. Unlike original BNF, angle brackets are not required. However, angle brackets may be used around a rule whenever their presence facilitates in discerning the use of a rule name, so you don't know it's a rule that's being talked about. This is typically restricted to rule name references in free-form prose, or to distinguish partial rules that combine into a string not separated by white space, such as shown in the discussion about repetition. So we'll try to remember that when we get to the discussion of repetition. We're going to look at variable repetition and specific repetition. The rule form, so rule name. But what's the structure of a rule? It's defined by the following sequence. So you'll have the name and then equals and then the elements. And then you have to have a carriage return and a line feed. CR, LF, line feed. Name is the name of the rule. Elements is one or more rule names or terminal specifications. A terminal is where it finishes, it ends. Things are either symbols or terminals, and CRLF is the end of line indicator, so that weird thing at the end is just the end of line indicator. The equal sign separates the name from the definition of the rule. The elements form a sequence of one or more rule names or value definitions, combined according to the various operators defined in this document, we'll get to them in a minute, such as alternative and repetition. For visual ease, rule definitions are left aligned. When a rule requires multiple lines, those continuation lines are indented. The left alignment and indentation are relative to the first lines of the A, B, and F rules and need not match the left margin of the document. Okay, so it's relative to the other lines. It's not absolutely left aligned. So we talked about rules, and we said that on the right-hand side of that equals sign, we're either going to have rule names, more rule names, or terminal values. Well, what are they? Well, the idea is that the rules ultimately resolve into, the same way that domain name is resolved into an IP address, into a string of terminal values, sometimes called characters. Okay, so rules, everything has to end at a terminal value. We'll see that in a moment. In ABNF, a character, that's just a non-negative integer. In certain contexts, the specific mapping of values into a character set, such as the American Standard Code for Information Interchange, that will be specified. And that's really helpful. We'll see that in this augmented BNF, they allow that, mapping the values into a character set. And we're going to see that we're going to use the percentage sign for every time we do that. Terminals are specified by one or more numeric characters. So a character is just a non-negative integer. We just specify terminals by using a numeric character. With the base interpretation of those characters indicated explicitly. What does that mean? So the following bases are currently defined. We've got B for binary, D for decimal, X for hexadecimal. Sadly not H. So BDX, let's have a look. So we might have CR. That's a rule name because it's to the left of the equals. And then we'll put percentage D 13, 13. So here what we're looking at is a terminal being specified by a numeric character. Let's look at another line. Percentage X 0D. Do we remember what that is? So we've got a decimal representation of a carriage return on the first line and a hexadecimal representation of carriage return on the second line. Okay. There's the terminal. There's the terminal, and we're specifying it on the right. It is also a rule name because it's on the left-hand side of the equals. So remember, 13 is the decimal name for a carriage return, and 0D is the hexadecimal. So that little x means we're using hexadecimal, and little d means we're using decimal. A concatenated string of such values is specified compactly, just using a period or a dot, to indicate a separation of characters within that value. Hence, CRLF, we put the two symbols together from ASCII, equals percentage D 13.10. ABNF permits the specification of literal text strings directly enclosed in quotation marks. Hence, command equals command string. Obviously, we're not having to go and get the ASCII code for C, O, M, M, A, and D there. Literal text strings are interpreted as a concatenated set of principal characters. And I've said, how else could they be interpreted? Well, you might think that you have to put some sort of concatenation mark, but it's just so it's reinforcing the fact that they are able to be specified directly, just like that in speech marks. And again, ABNF strings are case insensitive, just like rule names. But remember, here we're talking about terminal values, but same point about case insensitivity. Okay, so that's why we've got 13.10, because 13 is for carriage return and 10 is for line feed. So rule name equals ABC, rule name equals ABC. They'll match all those variations. To specify a rule that is case sensitive, specify the characters individually. I mean, that sounds really painful. Rule name equals percentage D97, percentage D98, all that, so you don't actually have to put percentage D each time. Will match only the string that comprises only the lowercase characters ABC. So we've made good progress now. We've talked about rule naming, rule form, and terminal values. Now a quick note on external encodings. External representations of terminal value characters will vary according to the constraints in the storage or transmission environment. Hence, the same ABNF-based grammar may have multiple external encodings, one for a 7-bit US ASCII environment, another for a binary octet environment, 8 bits, and still a different one when a 16-bit Unicode is used. Encoding details are beyond the scope of ABNF, although Appendix B does provide definitions for a 7-bit US ASCII environment, which most people use on the internet. By separating external encoding from the syntax, it's intended that alternate code encoding environments can be used for the same syntax. Okay. Now on to operators. Concatenation, which is just putting one thing after another with what looks like a space, is an example of an operator. There's no symbol, but it is an operator. A rule can define a simple ordered string of values, so a concatenation of contiguous characters by just listing a sequence of rule names. For example, foo equals percentage x 61. We're going to put a little comment. That's A. Call that B. Now wait for it, that's not the concatenation. Here's the concatenation. Mumble equals foo bar foo. So we're just listing the rules we've defined one after the other. And the rule mumble will now match the string ABA. And it does have to be lowercase because we've specified the lowercase a, the lowercase b. Linear white space. Concatenation is at the core of the ABNF parsing model. A string of contiguous characters values is parsed according to the rules defined in ABNF. For internet specifications, there is some history of permitting linear whitespace, space and horizontal tab, to be freely and implicitly allowing linear whitespace to be freely and implicitly interspersed around the major constructs, such as delimiting special characters or atomic strings. But this specification for ABNF does not provide for implicit specification of a linear whitespace. Any grammar that wishes to permit linear whitespace, you've got to do it explicitly around those delimiters. It is often useful to provide for such whitespace in core rules that are then used among the higher level rules. So what's being said there is that they're not going to sort out the whitespace for you. It's not sorted out. It's not done implicitly. You have to do it explicitly. That might sound bad. However, the way most people use ABNF is that you have some core rules that you rely on again and again. And so if you just put the whitespace in them, then that makes it a bit easier because you're going to use those rules again and again. The core rules might be formed into a lexical analyzer or simply be part of the main rule set. So that's concatenation. Now, what's this / about? It's about specifying alternatives. We use that to separate elements. Therefore, foo / bar will accept foo or bar. Note: a quoted string containing alphabetic characters, is that a literal that we looked at earlier? Remember that word command? I think it is. That is a special form, in fact, for specifying alternative characters, even though it's not got a /. And it's actually interpreted as a non-terminal, so a symbol. And it's either terminal or symbol. And it represents the set, think of it this way, representing the set of combinatorial strings with the contained characters, in the specified order, but with any mixture of upper and lowercase, because as we know, case doesn't matter. So it's just saying that technically under the hood, quoted strings are types of alternatives. I don't know where that comes in practice, but there we go. So concatenation alternatives. Now a little twist on alternatives, incremental alternatives. So an equals and a /. It's sometimes convenient to specify a list of alternatives in fragments. It's like an interrupted definition I've put at the top. So that is, an initial rule may match one or more alternatives, but then later rule definitions add to that set of alternatives. So maybe you can come back to a rule and say, oh, and also you can have this alternative and this alternative, and that equals / means I'm back at it now. And this is particularly useful for otherwise independent specifications that derive from the same parent rule set. So how would that work? The independent specifications, you use this equals / to say, actually, this is just carrying on, adding to the rule that's in the parent specification, and that would mean that they're somehow dependent on it, or it would communicate that actually this is part of something bigger. And they say this often occurs with parameter lists. ABNF permits this incremental definition through the construct, old rule equals / and then you put the additional alternatives. You're carrying on. So that the rule set alt1 there, and then we put rule set equals / alt3 to say we're carrying on. Rule set equals alt4, alt5. All that is the same as specifying rule set equals alt1 / alt2 all on the same line. Okay. Value range alternatives. Percentage C. Why is there a C? We've talked about D and X and B, B and D and X, but why C? A range of alternative numeric values can be specified compactly using a dash to indicate the range of alternative values. Hence, we might do digit equals, and now we're defining that rule, percentage X 30-39. And that's equivalent to the much more laborious digit equals and then listing all the alternatives like that. Why haven't they put an equals / on the second line there? Concatenated numeric values and numeric value ranges cannot be specified in the same string. So remember, concatenation involves a space, ranges involve a dash, So what do they mean? Cannot be specified in the same string. What? So you can't have a space and a dash together? A numeric value may use the dotted notation for concatenation. Did I say concatenation for dotted? Or it may use the dash notation to specify one value range. Hence, to specify one printable character between end-of-line sequences, the specification could be, so character line, %x, let's use hexadecimal, .0a, %x 20 to 7e, %x 0d to 0a, .0a. So I think the point there is that you can't put %x once, you have to put %x every time you shift between the dot and the dash, because they say concatenated numeric values and numeric ranges cannot be specified in the same string. So that's range alternatives. Now, rounded brackets for sequence groups. Elements enclosed in parentheses are treated as a single element, whose contents are strictly ordered. Thus, lm foo bar blat, where foo and bar is within rounded brackets, will match lm foo blat, or lm bar blat. But if you have lm foo / bar blat, you need to see how this is written, of course. Well, that will match lm foo or bar blat. So what was the point being made there? Okay. What might people think that matches in yellow? lm bar, you might think it matches lm bar or lm bar blat. Okay, so we take the lm and the bar. And why would they think that? They're being very reasonable. They think that the / means choose foo or bar. And why would they think that? Because that's how a slash works in English. It separates the word on either side in everyday English. Well, not with A, B, and F. We have the supreme slash. There's bar blat, and it divides the entire surrounding world into two parts. Is that the right way to think about it? Well, look at that slash. Does that divide everything after it into two things? Everything before it into one part and everything after it into another part? No. The point being made is really that the brackets are powerful enough to contain the slash as well. So really all it does is divide or have scope over the foo and the bar. So the slash is powerful, but not as powerful as the rounded brackets. They say it's strongly advised that grouping notation be used rather than relying on the proper reading of bare alternations, when alternatives consist of multiple rule names or literals. Hence it's recommended that the following form be used: lm foo / bar blat. So they're just marking it up with those brackets, but they don't have to be there. But it will avoid misinterpretation by casual readers. So don't rely on the supremacy of the slash. It's a bit like defensive driving. Don't rely on other road users to do the right thing. The sequence group notation is also used within free text, so the rounded brackets, to set off an element sequence from the prose. It's like distinguishing an element from the prose. Now on to variable repetition. Asterisk rule. The operator asterisk just before an element indicates repetition. The full form is A asterisk, then B, and then the element. Okay, B isn't the element to be repeated. You've got an asterisk and you can put a number before it and a number after it. Okay, A and B are optional decimal values, indicating at least A and at most B occurrences of the element. And the default values are 0 and infinity. So that if you put asterisk element, it allows any number including 0. One asterisk element requires at least 1. The expression is usually 1 or more. 3 asterisk 3 element allows exactly 3, because it's at least 3 and at most 3. But we'll see another way of putting at least 3 and at most 3 in a minute. And 1 asterisk 2 allows 1 or 2, because it's at least 1 and at most 2, which is 1 or 2. So that's variable repetition. You're saying it can be repeated a varying number of times, but you're of course setting limits on that. And it's contrasted with specific repetition. You can just put n in any element, and that's equivalent to having n as the lower bound and n as the upper bound. Okay, so you have exactly n occurrences for the elements. So 2-digit is a 2-digit number. 3 alpha is a string of 3 alphabetic characters. Alpha is a core rule, that uppercase word. That's why we're able to just put 3 alpha, same for digit. And that's it. So that's variable repetition and specific repetition. And actually, that 1 or more, you'll remember that 1 asterisk means one or more, and we're going to see someone called David Wheeler really doesn't like extended BNF because of the way it uses that 1 or more, and he says how most people are used to just using a plus for 1 or more. Now, optional sequences, square brackets enclose an optional element sequence, foo bar in square brackets. That's equivalent to *1 foo bar. Why? Because, as we saw, that means 0 or up to a maximum of 1. Okay, it's really default *1, even though there's nothing written there. And 3.9, comment, a semicolon starts a comment that continues to the end of the line. This is simply a way of including useful notes in parallel with the specifications. And then there's a precedence, so we can have 7 items in a sort of hierarchy. The mechanisms described above, we've now looked at all the operators. That's been section 3, operators. And the ones at the top of the list have the tightest binding, and then the loosest binding at the bottom. So rule name, that's got to have tight binding if you think about it. It would be chaos otherwise. Comment, value range, repetition, grouping, those rounded brackets, concatenation, just rule with a space, and alternative. Remember that the white space is explicit with A, B, and F, and then the alternative, that /, not a backslash. So we can now use this hierarchy to explain, because I know that it can be a bit strange at first talking about tight binding and loose binding, but we can use this to explain, in what sense does a rule name bind. But if we remember this slightly counterintuitive lm foo / bar blat, and we said most people would think that the / actually only concerns the foo and the bar either side. It doesn't concern bar blat, just the bar. But if we look at the hierarchy, we can see that concatenation has a tighter binding than the alternative. So the space, single space, has a tighter binding than alternative, which is a /. So that means that the force of association between bar and blat, I'm looking at the penultimate line over here, this binding association between bar and blat has a tighter binding, so higher up in the list, than /. So even though the / has a very weak binding, so even though the / does operate on bar blat on the one hand and lm foo on the other hand, it's so weak that it's not able to pluck bar from bar blat. So you shouldn't just think of weakness as operating over a smaller area. Weakness also manifests itself in not being able to overcome stronger forces, and that's why bar blat remains as a unit and lm foo remains as a unit. Concatenation has a stronger binding than alternative. Intuitively, most people think of tight binding as operating over a smaller area. You might think, first of all, it's relative. It doesn't really mean much to say tighter. You have to say tighter than what? Well, alternative doesn't have a tighter binding than anything. So that's the first point. And secondly, it's not about the area over which it exists. So something with a looser binding, that's like explanation for why the space between bar and blat binds tightly in the face of the alternative. Okay, alternative has relatively weak binding. So, back to the JMESPath specification. The grammar is specified using the ABNF described in RFC 4234. So we have expression equals sub-expression. Remember that term, sub-expression? Index expression, so / an alternative, comparator expression, okay, we use the incremental definition there, or expression, an identifier, a paren expression, asterisk, a multi-select list, a multi-select hash, a literal, a function expression, pipe expression, a raw string, a current node, and then we go on to sub-expression and say, well, what's that equal to? Expression dot, and then we've got lots of alternatives within that. An identifier, a multi-select list, a multi-select hash, and or a function expression, or a star. So that explains how a sub-expression is in fact being instantiated every time you see expression dot and then a multi-select list. That is a sub-expression, or something dot multi-select hash. So we weren't quite right when we were looking at those things earlier. And then we go and say, well, what's a pipe expression? Well, that's an expression or a pipe between two expressions, and then or expression at the end there at the bottom. So you can see what we're doing. All these things are being in turn defined. So pipe expression is up here. Well, what's a pipe expression? Sub expression is up here, and we're going and defining what a sub expression is. So it's as if we're analyzing into smaller constituents. However, pipe expression is itself defined in terms of an expression, so we can refer back. There is some recursiveness to it, and that's its advantage. So all these things are going to be discharged, or expression. Give that a tick. Here we say an AND expression, have two expressions either side of a double ampersand, ampersand, ampersand. So tick AND expression off. Dealt with that. Not expression. That's just a exclamation mark, then an expression. So we've said what a paren expression is. We've said what an index expression is. Give that a tick. And you can see it's made up of an expression, a bracket specifier, and then they've put / bracket specifier. So there's an alternative going on there. We know, don't we, that the weakest thing is an alternative, so it's not able to overcome the concatenation. So what's that operating over? Expression bracket specifier. I think that's right. All of the left hand side there. We move further down. Here's some more. We've got a multi-select list being defined, so give that a tick. And if we think back to what that was like, that makes sense. Yeah, it's got square brackets. You can see the opening square bracket and speech marks. We then have an opening rounded bracket, but they're not literally, because the rounded bracket isn't in speech marks. So we have an expression, and then a literal comma, and then we've got an asterisk before the comma expression. So what does that mean? You can have between 0 and infinity. So yeah, we saw that you can have a multi-select list with just one selector. So that asterisk means optional, basically. 0 or any number. Multi-select hash, again, you're going to have a literal opening curly bracket, a literal closing curly bracket, any number. Notice that asterisk, any number of comma, and then a key val expression. A key val expression. Think back to a multi-select list. A multi-select hash, well, you want to have a label in it and a selector, don't you? Label, :selector. So key val expression must be to do with that, but I don't know what that means. Oh, there it is, analysed below. So key val expression is an identifier, and then a colon, and then an expression. So that tells us that identifier, that means we have, that's where we put our label for the keys we want in the result. Bracket specifier. Okay, now this is being explained. Well, that is just a literal opening square bracket, then a number, or a literal asterisk, or a slice expression. Or you could just have a blanked square bracket. So we can see that this / here has scope over all of this on the left hand and all of this on the right hand side. Is that right? Yes, because all of this, oh no, let me see. So there's a literal opening square bracket. There's a literal closing square bracket. Yep, no, that's right, the supreme slash. Yep, okay, so that's been discharged. And it continues on to another line. And so we can see that a filter expression, that question mark, is just an example of a bracket specifier. Is that the right way to think about it? Fun fact, despite being an American standard, ASCII does not have a code point for the cent. It also does not support English terms with diacritical marks such as